All right, number 20. The figure at the right is an overhead view of a thin, uniform rod of length 0.8 meters and mass m rotating horizontally at an angular speed about an axis through the center. So you've got this. You've got this horizontal rod. The axis is through the center. What did I just say? I know that the length of the whole thing is 0.8 meters. It's got a mass of capital M. It's rotating horizontally at an angular speed of 20 radians per second. I'm assuming that's just initial. A particle of mass m over 3 initially attached to one end. So here's our little particle. It's got a mass of m over 3. Initially attached to one end is ejected from the rod and travels along a path that's perpendicular to the rod at the instant of ejection. If the particle's speed, Vp, so that's like after, right, is 6 meters a second greater than the speed of the end of the rod just after ejection, what is the value of Vp? Okay, so the idea is, so you've got this rod spinning around, right? So you've got this rod spinning around like this, right? Like a baton. Yeah. Okay? And there's a little thing attached to the end, right? Right? Now when it says it's ejected, it means literally like ejected. Like there must be some force, like maybe there's a little spring-loaded thing or something. Okay? So you're shrugging, like how do we know that? So how do we know that? If that was not the case, if it just fell off, what would be true about the velocity of the end of the stick and the velocity of the thing? They'd be the same, right? Like if I take, all right, so suppose I take Buzzy the bee and I spin around, all right? Suppose he's spinning at 6 meters a second, arbitrarily. All right, if I let go of him, then how fast is he going to be moving? 6 meters a second, right? But he'll just be going in a heads up. Oh, no, I'm not going to do that. He'll just be going in a straight line, right? Good? All right, follow? Okay? So, the idea is, so, after ejection, we've got the velocity of the particle is, what does it say, 6 more than the end of the stick? 6 meters a second plus the velocity of the end of the stick. Does that make sense?
Yeah. Okay.
Cool? So, what premise am I going to use to solve this thing? Conservation of angular momentum, right? Because there's no external torques, if you wanted to say it briefly, right? The idea is the rod is going to push the ball forward, the ball is going to push the rod backwards. Cool? Yeah. So the rod's going to slow down, the ball speeds up. Okay? So at this point, it's conservation of angular momentum. So let's see. So we need the angular momentum of the rod plus the angular momentum of the particle initially to equal the angular momentum of the rod final plus the angular momentum of the particle final. So, let's see, angular momentum of the rod is, what's the equation for I for a rod? I think it's 1/3 mr squared, where r is half of the length, right? Yep. Or you can do 1/12 the whole length, I don't remember which. Okay, so this is 1/3 m times 0.4 squared, right? So that's our I, times omega is 20. Follow? Okay, plus, let's see, the particle, it's got an inertia of mr squared, right? So m is m over 3. R squared is still 0.4. And omega is 20. Good? So I don't know that it's significant, but it turns out that the angular momentum of the rod is the same as the angular momentum of the particle. Cool? All right, so that's before. That's got to then equal the after. So the rod's not going to change, so it's going to be 1/3 m times 0.4 squared times omega f, right? There's two different omegas, though, aren't they? I can't use omega f over here for the particle, right? Do you guys see why or no?
No.
So right now, before the particle gets ejected, the particle is moving with the rod. So everything has the same angular motion. And then the particle gets pushed forwards. That's going to speed up its angular velocity, right? Newton's third law says the particle is going to push back on the rod, slowing down its angular velocity. Follow? So I feel like we need to do something with this that will allow us, because this is about linear velocity, but our equation here is about angular velocity. Yeah, I feel like we ought to just be able to divide by r, right? Okay, well, let's see what that does. So that means that, let's see, sorry, so let's see, the angular velocity, good question. Would r be the whole thing or half? Half, right? Because the circle has a radius of half. Okay, so let's see, the angular momentum of the particle is equal to the velocity of the particle over the radius, right? You guys agree with that? Yeah. All right. And the angular velocity of the stick is equal to the velocity, well, the angular velocity of the stick is equal to the velocity of the end of the stick over the radius. Oh, well, that's 6 plus, okay. Oh, wait a minute. Why am I dumb? What did I just do?
WP should be VS plus
Yes.
over R.
No, but I want to write it in terms of W.
Yeah.
My brain just totally paused here. What do I want to do? So this is the rod. I'm going to use stick. Oh, I switched between stick and rod, didn't I? That's part of what's confusing me. Let's use rod for R for rod. All right, this is final angle. Here, give me 1 second. So, all right, so here's our angular velocity of the rod after ejection. Everybody good with that? All right, plus, so this is m over 3 times 0.4 squared times the angular velocity of the stick. Good? Oh, dang it. Particle, 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 particle. There we go. Everybody good? All right, so does everybody agree with this? Yeah. So now we just need a way to resolve this, and because we've got two variables, right?
Yes.
And somehow we got to use this information to resolve that fact, right?
So you just put 6 plus VR into the first one.
Exactly. So I think we can just plug 6 plus the velocity of the rod over r, right?
Yeah.
And then we're good. So, yeah, and then everything's in terms of VR, right?
Okay.
Does that make sense? So now I've got just one variable.
Yes, I would definitely doesn't sense.
Follow?
Yep.
Systems of equations.
I hate this.
All right, so here we go. So before I go any further, I feel like we can simplify some of this. Everything has 1/3 m times 0.4 squared in it, right? 1/3 m times 0.4 squared. So all of this cancels out. Let me see. We can cancel everything in blue. 1/3 m times 0.4, 1/3 m times 0.4, 1/3 m times 0.4, 1/3 m times 0.4. Right? So now I'm looking at 20 plus 20 on one side, so that's just 40, equals, let's see, omega r is VR over r, plus omega p is 6 plus VR over r, and we actually know what our r is, right? So I think now it's just algebra. We plug in our 0.4. Isn't the radius 0.4? So 40 equals VR over 0.4 plus 6 plus VR over 0.4.
What happened to the M over like
Say it again, Peter.
because we. Oh wait, no. Okay, I'm good.
You see, I
Yeah.
canceled out all the
Yeah, I was
M
like
over 3s.
because the M over 3 next to WP like wasn't crossed out, so I like had to do some mental catch up. My bad.
No, you're okay. What didn't I cross out that I should have?
It-
Oh, this?
Yeah, it was just like
I gotcha. It's a sloppy cross-out job. There we go. Better?
thorough.
All right. Okay, so now you can solve for the velocity and then plug your VRs back into the other stuff and you're done.
Holy guacamole.
Yeah, holy guacamole, right? Sarah?
Like test-wise, is this more difficult?
Yeah, this one's definitely on the tough side.
Sorry, that was
Yes.
I'm gonna take